This is your presenter, Asloop Mudassar, and I am presenting slide number 18C of the course on atomic and molecular physics. In the today's lecture, I shall be covering hydrogen molecule, molecular orbital approximation, Hitler-London method, improvements in the approximations. This is actually a third lecture of the series on molecular physics. If you want to better understand this lecture, you should consult the previous two lectures also, that is 18A and 18B. H2 molecule. Second simplest method, second simplest molecule, 2 proton plus 2 electrons in hydrogen molecule, H2 molecule. The interaction between the two electrons have to be included. Because since the two electrons are present, their interaction, mutual interactions should be included also. As a consequence, wave functions into a product of one-dimensional functions cannot be written. So you see that we can, for the hydrogen molecule, we cannot write its wave function as a product of two atomic wave functions, because we have to include the interaction between the two electrons. No exact analytical solution even under clamped nuclei approximation is possible. So you see that this is the drawback associated with the H2 molecule, that when we solve the Schrodinger equation for the H2 molecule, we don't get any exact analytical solution even under the condition, even under the approximation that we are using a clamped nuclei approximation, in which the two nuclei are fixed by a distance capital R. And the approximate procedures are used. So since analytical solution is not possible, we have to use the approximate methods. And you know that in the 2 days lecture, I shall be discussing the two approximate methods, molecular orbital method and the Hitler-London approximate method. The two electrons with the same spatial functions are non-distinguishable and has to obey the Pauli principle. So you see that we cannot distinguish between the two electrons, because both electrons have the same spatial function and they are indistinguishable, and they have to obey the Pauli principle, that is, the electrons must have antiparallel spins. The total wave function has to be antisymmetric with respect to an exchange of two electrons. So you see that this is according to the Pauli principle. The exchange of two electrons would require that the wave function should be antisymmetric. For approximate calculations of the electronic states of the molecule, two approximations are commonly used. Molecular orbital approximation, which we shall abbreviate as MO, molecular orbital, MO approximation. The second one is the valence method, or the Hitler and London method, and simply we shall be talking about its name as Hitler and London approximation. The two methods are equivalent in their improved versions. So you see that these two methods, that is the molecular orbital method and the Hitler and London method, they will yield different results, and on the basis of these results we shall suggest some improvements in these two methods, and ultimately we shall see that when in their improved versions, both methods or both approximations will give you the same results. The two electrons attached to the two nuclei forming H2 molecule is shown on the next page. So you see that here I have shown the diagram for the hydrogen H2 molecule. You see that A and B are two nuclei. E1 and E2 are two electrons. E1 has been shown and is connected with nucleus A through the distance RA1, and E1 is also connected to the B through the distance RB1. Here 1 stands for electron 1 and B stands for nucleus B. Similarly, the electron E2 is connected with nucleus A by the distance shown as RA2 to 2 stands for the electron number 2, A stands for the nucleus. So our A2 is actually the distance of the electron 2 from the nucleus A. And similarly, electron 2 is at a distance RB2 from nucleus B. In addition to that one, we have also that electron, okay, you know that here I have shown that electron 1 is also be influenced by the nucleus B, electron 2 is also influenced by the nucleus A, and there is also a distance R12 between the two electrons. So the two electrons can have a repulsion between the two electrons. There will be a repulsive force between the two electrons, and the distance between the two electrons is R12. Similarly, there could be a repulsive force between the two nuclei, and the distance is capital R. Here we are again assuming that R is a relative, R is fixed. And on the same basis, we have fixed the value of R as we have used for in lecture number 2. Okay, so this is the general picture, you know, that of the hydrogen molecule. Now let's discuss the molecular orbital approximation in its simplest form. As R goes to infinity, that is if you separate out the two nuclei, nucleus A and nucleus B, that is R goes to infinity, the H2 molecule will split into two atomic hydrogens, that is atomic hydrogen A and atomic hydrogen B, because their separation becomes so large that each atom will, that is the atomic hydrogen A and atomic hydrogen B, will behave as individual atoms, and their corresponding wave functions phi A of R1 and phi B of R2 as the wave functions of atomic hydrogen A in its ground state, which is 1s state, and atomic hydrogen B, which is in its ground state 1s. You know that we have already discussed the hydrogen atom while we shall be discussing the atomic part of the course, and we have discussed that 1s is the ground state of the atomic hydrogen. A and B stand for the two nuclei, and E1 and E2 for two electrons. In molecular ground state, the approximate total wave function is given by. So you see that in the molecular orbital approximation, we are assuming that if R is so large that R approaches infinity, then H2 molecule will approach as if there are two individual atomic hydrogen atoms, HA and HB. Now, in molecular ground state, the approximate total wave function is given by. So you see that here we are assuming that the we are assuming a molecular state, and we are writing the total wave function of the molecular state as phi of R1 and R2 is equal to phi s of R1 and phi s of R2, where phi s is actually the symmetric wave function, and okay, both fs phi s are actually the symmetric wave functions as a function of R1 and R2. Where from equation number 18.35 from the previous lecture, we have that the symmetric wave function was equal to 1 over square root of 2 plus 2 times SAB, and then multiplied by the parenthesis containing phi A and phi B. This is what we have written. We have written the symmetric wave function for the two atoms. And you know that this was written when we were considering the hydrogen molecule, that is H2 singly ionized molecule, and for that one we wrote down the spherical wave symmetric wave function like this. And for the reference, you can consult equation number 18.35 from the previous lecture. The mutual interaction between the two electrons has been neglected. In the previous equation that we are writing, for example, in both of these equations, we have neglected the mutual interaction between the two electrons. The wave function is symmetric with respect to an exchange of two electrons. So you see that we have written symmetric wave functions. And here we are assuming that the wave function is symmetric with respect to an exchange of two electrons. But in reality, the wave function must be antisymmetric. To make it antisymmetric as required by the Pauli principle, because we have two electrons in the same molecule in the same ground state, one as are the ground states of the two electrons, then of course the spin function, since to make it antisymmetric as required by the Pauli principle, the spin wave function must be antisymmetric, because the wave function will consist of the spatial part, and you know that we have considered the spatial part to be consisting of symmetric wave function phi s of R1 and phi s of R2. So the spatial part has been assumed as a symmetrical. It means that we should include the spin as the antisymmetric wave function. So the total wave function including the spin becomes phi of R1, R2, S1 and S2. That is, a wave function is a function of R1, R2, radial distance R1, R2, and the spin wave functions S1 and S2. And now it is on the right hand side, we have written the product of two symmetric wave functions, phi s of R1 and phi s of R2, as we have written previously. Now we are going to multiply the spin function, and we have chosen the spin function as an antisymmetrical function due to when there is an exchange of two electrons. This part of the spin wave function becomes antisymmetric, and this wave function is given by a square root of 2 divided by 2 and multiplied by a square bracket containing a chi plus of 1 of electron 1 multiplied by chi minus of electron 2 minus chi plus of electron 2 and chi minus of electron 1. This negative sign between the two terms will ensure that the wave function is an antisymmetric wave function. So you see that chi plus will represent a state when the electron has a spin up, and chi minus will indicate a state when the electron has a spin down. So here these are the combinations of spin up, spin down. Spin up, that is in the first term, indicates that the electron 1 has a spin up, the electron 2 has the spin down, and then with a negative sign we have the electron 2 with the spin up and electron 1 with the spin down. So we have actually this square bracket contains actually both possibilities, that electron 1 could have spin up and electron 2 could have spin down, and the other possibility is that electron 2 has a spin up and electron 1 has a spin down, and we have combined these two possibilities with a negative sign so that the wave function becomes antisymmetric. So this is a spin wave function with antisymmetric nature. Now you see that the total wave function phi of the molecular orbital approximation under molecular orbital wave function has been written such that there is a multiplication of two symmetric part of the wave functions and also with the spin antisymmetric wave function. Now, in order to write this one in the simplest form, we are just going to introduce some parameters. That is, chi plus will be represented by alpha, chi minus by beta. So it means that alpha will represent a spin with the spin up and beta will represent spin down. And phi a of I, that is the wave function phi a, will be represented simply by a, and the wave function phi b will be simply represented by small b. And I could be 1 and 2. 1 mean that we are considering electron 1 and 2 mean that we are considering electron 2. So alpha of 1 means that we are considering the particle 1 to have spin up, that is ms of particle 1 is equal to plus half, and beta 1 means that we are considering the second particle with the ms of particle 1 is equal to having a minus half. So alpha stands for spin up and beta will stand for spin down, as we have defined over here, that is chi plus is equal to alpha and chi minus is equal to beta. Here we have defined alpha and beta, that alpha will represent spin up and beta will represent spin down. Now the equation number 18.57 can simply be reduced under these parameters, that phi of R1 and R2 is equal to 1 over 2 plus 2 times of SB, and then we have in the multiplication we have A of 1 plus B of 1 multiplied by the square bracket containing A of 2 and B of 2. And here we have considered only the special part, and we have so far neglected the spin antisymmetric wave function while writing equation number 18.58. The total wave function, including the spin part, can be written as the Slater determinant. So phi of R1, R2, S1, and S2 is equal to Slater determinant containing first row as phi S of 1, alpha of 1, and phi S of 2, alpha 2. And the second row contains phi S of 1, beta of 1, phi S of 2, and beta of 2. So you see that if you consider column wise, phi s of 1 is present in the column, and in the second column we have a phi s of 2 present in the column. So if you expand this determinant, you will ultimately get this wave function that is shown in 18.57. With abbreviations or with the introduction of these parameters, the simplified version of equation number 18.7 is given by the determinant shown as equation number 18.59. The total energy of the two electrons in the rigid hydrogen molecule is then can be written as, you see that we have written the wave function for the rigid H2 molecule, and now we are going to write down the total energy of the H2 molecule. So the total energy E of the H2 molecule will be equal to the summation over kinetic energies of the individual particles, because I stands for particle 1 and particle 2, for example electron 1 and electron 2, plus the potential energy of the system. So this total energy of the H2 molecule written on the left hand side as E is equal to the summation over all kinetic energies of the particles plus the potential energy of the system. So you see that now under this condition we can write down the Hamiltonian of the rigid H2 molecule with the clamped nuclei. That is, the separation between the nuclei is fixed by the distance capital R. Under that condition we can write down the Hamiltonian of the rigid H2 molecule. So H hat is actually the Hamiltonian operator written on the left hand side is equal to minus h bar square over 2m, where m is the mass of the electron, and the parentheses contain del 1 square plus del 2 square, where del 1 is the del operator associated with the electron, and del 2 is the operator associated with electron 2. And then we have the potential energy term, which is plus E square over 4 pi epsilon naught, and the parenthesis contains minus 1 over R A1 minus 1 over RB1 minus 1 over RA2 minus 1 over RB2 plus 1 over R plus R12 plus 1 over capital R. You know that these negative terms are the terms which produce attractive potential. So minus 1 over RA1 will produce is the attractive potential term. Similarly, minus 1 over RB1 is the attractive potential term. Minus 1 over RA2 is the attractive potential term. Minus 1 over RB2 is the attractive potential term. And plus 1 over R12 is actually the repulsive term. Due to the repulsive force between due to the two electrons, and then we have 1 over R again producing a repulsive term due to the repulsive force between the two nuclei. And you know that when I am writing RA1, it means that I am writing the separation or the distance of the electron 1 from nucleus A, and R1 being mean RB1 means that the electron 1 is at a distance from the nucleus B, and RA2 means that the electron 2 from nucleus A. RB2 means electron 2 from nucleus B, and R12 mean that is the separation between electron 1 and 2, and the capital R mean that is the separation between the two nuclei. So you see that we have proposed a Hamiltonian of the hydrogen molecule under the rigid condition or under the clamped nuclei condition where capital R is fixed. Now let's simplify this one by introducing the abbreviation that H Hamiltonian as Hi is equal to minus H bar square over 2m del I square. So here you see that I am introducing Hi operator, Hamiltonian operator, to be equal to minus H bar square over 2m into del I square plus E square over 4 pi epsilon naught, and within the parentheses I have a minus 1 over RA1 minus 1 over R minus 1 over RAI minus 1 over RBI plus 1 over capital R. So you see that if I introduced this Hi operator, I can write equation number 18.61, this equation, in the simplified version as shown in equation number 18.63. That is H operator is equal to H1 Hamiltonian operator plus H2 Hamiltonian operator plus E square over 4 pi epsilon naught containing and parenthesis containing 1 over R12 minus 1 over capital R. So H1 operator can be considered as the operator, as the Hamiltonian operator of a single atomic hydrogen atom. Similarly, H2 Hamiltonian operator can also be considered as the operator of an individual atomic hydrogen atom. Okay, and then we have this term which is E square over 4 pi epsilon naught and containing parenthesis containing 1 over R12 minus 1 over capital R. Here I have written H1 operator and H2 operator, and you should not confuse them with the Hamiltonian operator of the atomic hydrogen atoms. These are just the labels that I have given over here: H1 Hamiltonian operator and H2 Hamiltonian operator. And you see that this operator, Hamiltonian operator defined in equation number 18.62, is actually the Hamiltonian operator of the hydrogen singly ionized molecule. So each H1 operator, H1 Hamiltonian operator and H2 Hamiltonian operator as defined in equation number 18.62 actually represents the Hamiltonian operator of the single hydrogen singly ionized molecule. So I can combine H1 operator and H2 Hamiltonian operator as twice the Hamiltonian operator of the hydrogen singly ionized molecule, and plus delta E is actually the energy difference, energy term. Delta E actually the energy term defined by E square over 4 pi epsilon naught, and the parentheses contain 1 over R12 minus 1 over capital R. Okay, and you see that this term, which is the Hamiltonian of the hydrogen singly ionized molecule, has been defined previously, and I have reproduced over here. That is the H operator, Hamiltonian operator for the singly ionized hydrogen molecule, or the hydrogen, or the molecular, or the ionic hydrogen molecule, is equal to minus H bar square over 2m into del E square minus E square over 4 pi epsilon naught, and the parentheses contain 1 over Ra plus 1 over Rb minus 1 over R. So the electron has been referenced with respect to nucleus A and with respect to nucleus B, and there is also a repulsive force, and there is also a separation between the two nuclei, which is 1 over capital, which is capital R. So H hat, which is the Hamiltonian operator for the hydrogen singly ionized molecule, is the Hamiltonian of the hydrogen molecule ion. And delta E is equal to E square over 4 pi epsilon naught and multiplied by the parenthesis containing 1 over R12 minus 1 over capital R. Actually is the difference between the Coulomb repulsion. So this is actually the difference between the Coulomb repulsion between the two electrons and the two protons, because 1 over R12 is actually the repulsion term between the two electrons, and 1 over r is actually the repulsive term between the two protons, and this negative sign is actually give you the difference. So this is the difference between the Coulomb repulsion between the two electrons and the Coulomb repulsion between two protons. The energy E of R of the ground state H2 molecule. The energy E of R of the ground state H2 molecule is twice the energy of the H2 singly ionized ion plus the energy of the electron repulsion minus the nuclear repulsion. So you see that this paragraph which I have given actually defines this whole term. So the potential energy curve E of R of the ground state hydrogen molecule. So look at this one. We are talking about the energy E of R. That is the potential energy of the ground state of the H2 molecule is twice the energy of the H2 singly ionized molecule plus the energy of the electron repulsion minus the nuclear repulsion. That is, we have all defined all the three terms. That is, we have defined the energy corresponding to the Hamiltonians, and we have also defined the energy delta E. The corresponding potential curve has a minimum at R is equal to RA is equal to 0.7 angstrom, where R is actually the equilibrium distance, or the distance at which the potential energy becomes minimum. So if you choose R is equal to RA, then you get this value equal to 0.7 angstrom. The electron and the nuclear repulsion cancel each other at R is equal to 1 angstrom. That is the two terms. That is 1 over R12 minus 1 over R. These two terms could cancel each other at R is equal to 1 angstrom. At the minimum position R is equal to RE of the hydrogen molecule, they give only a small negative contribution to the total energy. So this energy term delta E that I have defined for the hydrogen molecule at its equilibrium distance will give you a small negative contribution to the total energy of the system. And you know that the total energy I have defined as E of R, which is the potential energy term. And you know that this E of R is actually the potential energy term which varies with the distance R. But when we are talking about the binding energy, then of course we are talking about the value of E at R is equal to RE. So E of R at R is equal to RE will give you the binding energy. Otherwise, this equation will represent the potential energy curve. The binding energy of the hydrogen molecule is slightly smaller than 2 times the binding energy of the hydrogen singly ionized molecule. So this binding energy of the hydrogen molecule is slightly smaller. It means that the hydrogen molecule is more stable in comparison with the hydrogen singly ionized molecule in the Lekau approximation. So in the Lekau approximation, the binding energy of H2 molecule is slightly lower than the binding energy of the binding energy equal to twice the binding energy of the hydrogen singly ionized molecule. And we can calculate this one, that is the binding energy of the hydrogen molecule is equal to twice the binding energy of the hydrogen singly ionized molecule plus delta E. And this will give you minus 2.7 electron volt. You see that I have written these binding energies similar to the pattern given in equation number 18.63. On the right hand side, you can see that I have 2 times the Hamiltonian operator operating on the hydrogen singly ionized molecule plus delta E. So the energy corresponding to this one has been written, and also the corresponding energy delta E has been written. So I have written that the binding energy of the hydrogen molecule is equal to 2 times the binding energy of the hydrogen singly ionized molecule plus delta E. And the energy of this one is the combined energy of these two is equal to minus 2.7 electron volt. So now let me show you the curves giving us the plot of potential energies and also binding energies also. So you see that in this curve I have plotted the dotted curve, black dotted curve is actually the plot of the potential energy of the H2 singly ionized molecule. And the green function and the green curve is actually the potential energy curves of the hydrogen molecule, which we are currently discussing in this lecture. And the red curve is actually the potential energy corresponding to twice the energy of the hydrogen singly ionized molecule shown in dotted. So if you multiply the dotted curve by 2, you will get the curve red. I have also plotted the function 1 over R12 minus 1 over capital R. You see that this function, when the value of R is small, the value of this function is small, but you increase the value of R, that is when you increase the separation between the two nuclei, which is shown in the R as a function of the angstrom, then of course you will see that this curve takes increasing values, and then of course it becomes slightly then flattened, not flattened, but its increase becomes smaller. And on the vertical side I have shown 13.6 electron volt as the ionization potential energy of the individual hydrogen atom, then of course 0 energy, then minus 13.6 electron volt is the binding energy of the single atomic hydrogen atom, and then its twice value, which is minus 27.2. So you see that the binding energy here is the binding energy of the H2 molecule, which is the minimum energy. The minimum of the potential energy curve will give you the binding energy of the H2 molecule, which is this. And you know that the binding energy corresponding to twice the value of the hydrogen molecule, singly ionized molecule, is this at this point, at the minimum of the red curve. And the minimum of the green curve is lower than the minimum of the red curve by a distance of 2.7 electron volt, which I have mentioned over here, minus 2.7 electron volt. Because you know that here I am comparing the binding energies of the twice the value of the hydrogen singly ionized molecule and the binding energy of the hydrogen molecule. The difference between them is minus 2.7 electron volt. And here you can see that the green curve, that the minimum of the green curve is lower than the minimum of the red curve by minus 2.7 electron volt. So let me read the caption of this figure also. You know that on the vertical side I am plotting the energy in electron volt, and on the horizontal side I am plotting the separation between the two nuclei capital R as a function of capital R, and capital R has been given in terms of angstrom. And the caption is comparison of potential curves of the singly ionized hydrogen molecule and the hydrogen molecule, and the third term belongs to the molecular orbital Lekau approximation. Now you see that I am going to explain this further, but let me read the paragraphs over here. Experimental value EB differs by minus 4.7 electron volt. So you see that I have not plotted the experimental value over here. But if you consider, you will find that the binding energy differs from the experimental value by a value of minus 4.7 electron volt. Comparison of different potential curves are shown. That is a potential curve corresponding to singly ionized hydrogen molecule, potential curves for the hydrogen molecule, and the potential curves for the molecule which is equal to twice the hydrogen singly ionized molecule. These three potential curves have been shown. A serious drawback of the Lakau approximation is the wrong behavior of E of R for R goes to infinity. For example, if you consider the hydrogen molecule, the green curve, this green curve is actually going to give you a wrong result when R goes to infinity, because this H2 molecule should converge similar to the convergence of red curve. But you know that H2 molecule has a separation, much separation from the red curve at R goes to infinity. So you see that this is what a serious drawback due to the Lakau approximation, that the H2 curve should at a large value of R should behave as a should behave as that of as that there will be no binding energy over here. Okay, a serious drawback of the Lakau approximation is the wrong behavior of E of R for R goes to infinity. Detailed calculations give that E at R goes to infinity is equal to 22 point divided by 16 times the binding energy of the hydrogen atom. Binding energy of the atomic hydrogen atom. And you know that the binding energy of the atomic hydrogen atom is actually 13.6 electron volt. So when R goes to infinity, we get this value. That is the binding energy approaches to a value of 22.16 times the binding energy of the hydrogen atom. And you know that the binding energy of the hydrogen atom is 13.6 electron volt. So we should have this result, which the green curve is not producing. Detailed calculation gives this. Instead of 2 times the binding energy, 2 times the binding energy of the hydrogen atom when it is ionized, twice of that one. You know that the binding energy of the atomic hydrogen is minus 13.6 electron volt. So what should be the behavior of the hydrogen molecule? What should be the behavior of the potential energy curve of the hydrogen molecule? That is what should be the behavior of the green curve? You know that when you set the value of R goes to infinity for the green curve, you will get this value 22.22 divided by 16 times the binding energy of the hydrogen atom. And you know that the binding energy of the hydrogen atom is minus 13.6 electron volt. And this factor 22 divided by 16 indicates that the binding energy of the hydrogen molecule under the Lakau approximation approaches this value, which is 22 divided by 16 times the binding energy of the hydrogen atom. That is, this curve should be slightly lower than the 13.6 electron volt and should approach to that line. So you see that actually in principle, the green curve which is for the hydrogen molecule, should approach a value of 2 times the ionization potential of hydrogen atom, that is minus 27.2 electron volt. So this green curve H2 curve for large values of R should approach a line with a value of minus 22 minus 27.2 electron volt, which is twice the value of minus 13.6 electron volt. So green curve should approach a line corresponding to minus 27.2 electron volt, but you know that apparently it is not approaching like that. So this is the main drawback of the Lekau approximation, that the curve of that the potential curve of the hydrogen molecule is not approaching a value of minus 27.2 electron volt at a large value of R corresponding to infinity. So you see that this is the major drawback of the hydrogen of the Lekau approximation that we have dealt with in order to find out the previous discussion. The molecular orbital approximation requires improvement. Of course, improvements is required because you know that the curve is producing a practical value of 22 divided by 16 times the EB, that is the binding energy of the hydrogen atom. And you know that this factor is slightly lower than minus 13.6 electron volt. But you know that the green curve should not approach this value. Instead, it should approach a value which is twice the ionization potential of the hydrogen atom. And this value becomes equal to 27.2 electron volt. So the green curve at an infinite value of R should approach this value minus 27.2 electron volt, which is not approaching like that. And it is not approaching like that. It means that there are some serious drawbacks with the Lekau approximation. So the molecular orbital approximation requires improvement because these are the results we have produced according to molecular approximation. Let's first discuss the second approximation. So you see that before I discuss the approximation, I discussed the refinement or improvement in the molecular orbital approximation. I want to discuss the second approximate method, second approximation next. And this is the Hitler-London method. The ground state molecular orbital H2 molecule contains 2 electrons with opposite spins according to the Pauli principle. The corresponding wave function can be written as phi1 is equal to C1 and phi A of 1 and phi B of 2, which means that the electron 1 is with the nucleus A and electron 2 is with the nucleus B, and this is some constant C1. This gives the probability amplitude that the electron 1 is at nucleus A while the electron 2 is at nucleus B, and are respectively defined by the wave function phi A of 1 and phi B of 2. As the two electrons are indistinguishable, the wave function leading to the same charge distribution takes the form. So you see that we can also write the wave function equivalent to the wave function 1 phi 1 as phi 2, and phi 2 is equal to C2 times of phi A 2, phi A of 2 and phi B of 1, where the particle 2 is with atomic function A and particle 1 is with wave function B. So you see that both are the possibilities. Phi 1 and phi 2 are the two possible conditions that we can write down under the Hitler-London method. So you see that it is better to combine the two to give you a comprehensive wave function. According to the Pauli principle, the spatial part of the wave functions must either be symmetric or antisymmetric with respect to electron exchange. The total spatial part of the normalized wave function can be written as a linear combination of a phi 1 and a phi 2, with the C1 is equal to plus minus times C2. So if there is a plus sign, it means that we are talking about the symmetric wave function, And when there is a negative sign with the C2, we are talking about the antisymmetric wave function. So C1 is equal to plus minus a C2, and we can set the two values equal to C. So we can use a single parameter C, a single constant C. So we have a wave function phi of SA, where S stands for the symmetric case and A stands for the antisymmetric case. So phi of SA is equal to phi 1 plus minus phi 2. For the symmetric case, we shall assume positive sign. For the antisymmetric case, we shall assume negative sign. So you see that the comprehensive wave function covering both symmetric and antisymmetric situation is given by the right hand side, which is equal to C times the square bracket containing phi a of 1, phi b of 2, plus minus phi a of 2 and phi b of 1. So you see that this is the comprehensive wave function that we have written under the approach, under the Hitler-London method. And you know that C is what we have already determined in the second lecture. So phi A and phi B are already normalized, which gives C, the constant C is equal to 1 over square root of 2 multiplied by the square root of 1 plus minus SB square, where you know that SB is the overlap integral defined in the previous lecture. Thus the wave function obtained by the Hitler and London is phi subscript is S and A. S stand for symmetric, A stand for antisymmetric, and HL as a superscript stands for Hitler and London, and phi is the wave function. So the wave function phi under Hitler and London method is equal to 1 over the square root of 2 times the square times the parenthesis containing 1 plus minus square of SAB, and then we have a square bracket containing A of 1 times B of 2 plus minus A of 2 and B of 1. So you see that this is the comprehensive wave function that we have written under the Hitler-London method. Now comparison between the two approximations. One approximation is the molecular orbital approximation. The other approximation is the Hitler-London approximation, because they are writing wave functions for the H2 molecule and assuming some approximations. That's why these are called the two approximations, molecular orbital and hydrogen molecule and hydrogen and Hitler-London approximations. Let's compare the two approximations. And after comparison, we shall suggest some improvements in the two approximations, and we shall see there that the improvement in the two approximations will yield nearly identical results. The molecular orbital approximation gives a H2 wave function, which neglects the mutual repulsion between the two electrons. So you see that this was one of the drawbacks of the molecular orbital approximation, that we are writing a wave function for the hydrogen molecule, but at the same time we are neglecting the mutual repulsion between the two electrons. And this has been explained in equation number 18.58 and 18.59. And I have reproduced this wave function due to the molecular orbital approximation given in equation number reproduced in equation number 18.70 and 18.71. This is what we have already discussed, these two forms of wave functions for the molecular orbital approximation for the hydrogen molecule. So you see that these are two forms of wave functions of the hydrogen molecule under the molecular orbital approximation. Now next we want to give you the Hitler-London wave function. In Hitler-London method, both electrons are regarded, that is, are considered from the beginning, and the molecular orbital is written as the product of two atomic orbitals. The final wave function is actually a linear combination of the two products. So let's talk about the Hitler and London method. We have also given in one of the previous equation, that in equation number 18.69, I have given the wave function of the Hitler and London method. Now you see that here I am going to only I am considering the spatial part of the wave function. You see that in the Hitler-London method, which was presented in equation number 18.69, I have only considered the spatial part of the wave function, and I have not considered the spin part of the wave function. Whereas the molecular orbital wave function given in equation number 70 and 71 consider both the spatial part and the spin part of the wave functions. So the intermediate step between the last two equations, which also follows from equation number 58, is given by. So you see that we can write the wave function in this form: phi of r1 and r2 is equal to 1 over 2 plus 2 times SAB, and multiplied by the two square brackets containing a of 1 plus b of 1 and a of 2 and plus b of 2. And this wave function has been discussed in equation number 58. And this was actually giving you an intermediate point while you switch on from equation number 70 to equation number 71. So this can also be written as, under the multiplication of the two square brackets. So this is the spatial part of the wave function of the hydrogen molecule under molecular orbital approximation. And you know, if you multiply the two square brackets, you get this wave function. This is the spatial part of the molecular orbital wave function. You know that we have the spatial part of the wave function due to Hitler and London given in equation number 69. So we are also reproducing the spatial part of the molecular orbital wave function for the hydrogen molecule, which I have given in equation number 73. And at the same time, I have reproduced the wave function due to Hitler-London approximation shown in equation number 74, so that I can compare the wave spatial part of the wave function given by the molecular orbital and the spatial part of the wave function given by the Hitler and the London approximations. These two wave functions have now been given as equation number 73 and 74 respectively. And we can very easily compare the two wave functions. Comparing the last two equations, it is found that the first two terms in the wave function of the Hitler and London are missing. You know that there are two terms, a of 1, a of 2 plus b of 1 and b of 2. These two terms are missing in the Hitler and London wave function. This describes the situation where both electrons are simultaneously at nucleus A and nucleus B. That is where you have H ionized, H as singly ionized, positively ionized, and H minus ionized. So we have a hydrogen atom positively ionized and negatively ionized. The product of these two functions actually correspond to the case that the two electrons are either with nucleus A. So A of 1 and A of 2 means that the electron 1 and electron 2 are both with nucleus A. And the case B of 1 and B of 2 indicates that the electron 1 and 2 are both with nucleus B. You know that in either of these cases, we have the product of H positively ionized and H negatively ionized. The product of these two functions depict the condition that the both electrons are either with the electron with the nucleus A or with the nucleus B. So when only the order will change when they are associated with the nucleus B. So you have the product of two singly ionized, one positively ionized, the other negatively ionized. The product of these two ions actually means that the two electrons are either with the nucleus A or with the nucleus B. And you know that this is not a condition shown by the Hitler and London method. In a molecular orbital, the configuration has the same weight. So you know that both of these one, that is particle 1 with A, particle 2 with B, and similarly particle electron 2 with the nucleus A, electron 1 with the nucleus B, their weights are equal because their coefficients are equal. The ionic form, and you know that these has slightly different weights comparison because of the constant present in the Hitler and London method. So the constants, you know, they are different. So they have different weighting factors, but you know that the terms are the same. The electronic form is completely neglected. The ionic form is completely neglected in the Hitler-London method or approach. That is, we have the situation that give the ionic form, which is the product of the hydrogen positively ionized and negatively ionized. This ionic form is completely neglected by the Hitler and London method because this ionic form results from the first two terms of the molecular orbital wave functions shown in equation as the first two terms in equation number 73. So the ionic form is completely neglected in the Hitler-London approach, whereas it is overemphasized in the molecular orbital approach. So the ionic form is completely neglected in the Hitler-London approach, whereas it is overemphasized in the molecular orbital approach. So these, you know that this is our finding when we are comparing the two wave functions. That is the wave function of the hydrogen molecule due to molecular orbital approach and due to the Hitler and London approach. To find a comparison of the molecular binding energies from the two methods, let's rewrite the Hamiltonian. And this is also given in equation number 61. So I am writing from equation 6 number 1, rewriting the Hamiltonian in the following form. So the Hamiltonian can be written as Hamiltonian of the purely corresponding to electron 1, which is minus h bar square over 2m del 1 square minus e square over 4 pi epsilon naught into RA1, where RA1 indicates that the electron is connected with the nucleus A. So this is the first parenthesis indicates that it is the Hamiltonian purely of the electron 1 associated with the nucleus A. And then second parenthesis, which is minus h bar square over 2m del 2 square minus e square over 4 pi epsilon naught times RB2, which means that the electron 2 is connected with the nucleus B. So this is the Hamiltonian. This is the Hamiltonian of the electron 2 connected with the nucleus B. And then I have the third term, which is minus e square over 4 pi epsilon naught, and the parentheses contain 1 over RA2 plus 1 over RB1 minus 1 over R12 minus 1 over capital R. You know that the first two brackets in equation number 18.7 can be written as Hamiltonian of due to nucleus A plus Hamiltonian due to nucleus B minus Hamiltonian due to both nucleus A and B. Because the first parenthesis shows that it is that as if it is the Hamiltonian of the atomic hydrogen with the nucleus A, and the second parenthesis shows the Hamiltonian as HB, which means that as if it is the Hamiltonian of an atomic hydrogen containing nucleus B. And then we have the third term with the negative sign HAB containing both nuclei. Because you know that when you consider both nuclei together, you consider the repulsive force due to two electrons, and the term is 1 over R12, and the this is the repulsive force between the two electrons due to R12, and 1 over R gives you the repulsive force between the two nuclei. And also there are two terms, that is the particle electron 2 is also connected or influenced by the nucleus A, and this RB1 means that the electron is also connected with the nucleus B. So you see that this is all these four terms indicate the interaction between the two electrons, between the two nuclei, and between the electron 1 with the nucleus B and electron 2 with the nucleus A. And the Hamiltonian, corresponding Hamiltonian is shown as or labeled as a Hamiltonian of the nucleus AB together. So you see that we can depict the two configurations included in the molecular orbital approximation with equal weights as. You know that on the figure on the left means that the two electron E1 and the electron E2 are coupled with the nucleus A. And the so nucleus A is negatively charged because it, in addition to its neutral hydrogen atom, it has also got one more negatively charged electron. And then you have nucleus B. Since nucleus B is missing its electron, so it is positively ionized. So electron here is A is negatively ionized and B is positively ionized. Similarly, another condition can also hold when both of these electrons are combined with or coupled with the nucleus B. In that case, the nucleus B will be negatively ionized and the nucleus A will be positively ionized. So I have shown only one part of that one where both electrons are with the nucleus A and no electron is with the nucleus B. Now there is the second part on the right hand side where electron 1 is with the nucleus A and the electron B is with the nucleus B. So I have shown both of these conditions. And you know that the two terms HA and HB corresponds to the right hand side figure, whereas the term HAB, Hamiltonian with the molecule A and B, is the term depicted on the left hand side of the figure. So let's see in words. Here the Hamiltonian of the hydrogen molecule is under the molecular orbital is written as the sum of atomic Hamiltonians HA and HB of the two atomic hydrogen, and the third term HAB, Hamiltonian of the HAB, which contains the attraction of electron 2 by nucleus A due to this term, and the attraction of electron 1 by nucleus B due to this term, and the mutual repulsion between two electrons due to the term containing R12, and the mutual repulsion between two nuclei containing due to the term capital R. Inserting this Hamiltonian of the rigid H2 molecule into the Schrödinger equation H5 E5, the total energy can be written as. So you see that we have discussed in detail the Hamiltonian of the hydrogen molecule due to the molecular orbital, and now we are putting that wave function in the Schrödinger wave equation H5 is equal to E5, and then the E is which is the total energy, which is the eigenvalue energy of the function is given in equation number 77. So E total energy of the hydrogen molecule is equal to E of A, which is equal to the energy of the hydrogen molecule due to nucleus A plus energy of the hydrogen molecule due to nucleus B plus delta EB. Where E of A and E of B are the energies of the two separated atoms A and B. These are in fact the polar potential energy curve, potential energies of the due to nucleus A and nucleus B. and delta EB, which we have found equal to energy, potential energy of H2 molecule minus 2 times the potential energy curve of the hydrogen atom. And you know that this delta EB is also obvious if you replace E of A by E of H and E of B by E of H, then E of H due to E of A and E of H due to E of B will combine together, will give you 2 times E of H. And this E on the left hand side is actually the energy of the hydrogen molecule, can be written as E of H2. So on the left hand side you have E of H2, and on the right hand side, due to these two terms, you have 2 times of E of H. So ultimately delta EB can be written as E of H2 minus 2 times E of H. A stable molecule is formed when delta EB is less than 0. That is the difference of binding energies is less than 0, is negative. Then we can say that a stable molecule is formed. And due to that one, we have E of H2 is less than twice the E of H1. That is the energy, that is the total energy of the that is the potential energy of the hydrogen molecule should be slightly lower than the twice the energy of the individual hydrogen atom in atomic form. That is, the energy of the molecule is less than the sum of the ground state energies of the separated hydrogen atoms. And for delta EB greater than 0, the potential curve becomes repulsive. That is, when delta B is greater than 0, we shall have a curve which is repulsive in nature. For R goes to infinity, delta EB as a function of R goes to 0. Solving the Schrodinger equation using the wave function of the Hitler and London, we are using, and you know that we shall use this condition while solving this Schrodinger wave equation, that delta of EB as a function of R should approach 0 when R goes to infinity. So you see that let's solve next the Schrodinger wave equation using the wave function of the Hitler and London, and the equation is H of H phi is equal to E phi, and here phi is actually the wave function due to Hitler and London. So when you solve this one, you will get the energy as a function of R to be equal to the integral of conjugate of the spherical wave function as a function of R and capital R, and there is a Hamiltonian due to, and this Hamiltonian is actually the Hamiltonian I have shown in this equation, and then the wave of symmetric wave function phi s as a function of R and capital R integrated with respect to d tau. D tau has been explained in the previous lecture. So you see that this is the potential energy equation as a function of R for the case of the Hitler and London approach, whereas the total potential energy due to the for the case of the molecular orbital is shown in equation number 77. This gives a binding energy delta E as a function of R, as a function at R is equal to RE, where RE is the equilibrium distance, that is the distance at which the potential energy becomes the minimum, and also at this value of R we have the energy which is called the binding energy. So this gives the binding energy delta E, at R is equal to RE to be equal to minus 3.14 electron volt, which is closer to the experimental value, and the experimentally found binding energy is equal to delta EB is equal to minus 4.7 electron volt. And you know that this energy due to the which we have computed using the Hitler-London model is minus 3.14 electron volt, close to experimental value of minus 4.7 electron volt. So this is closer to the experimental value this than the value predicted by the simple Lekau method or simple molecular orbital Lekau approximation using the overemphasized ionic configuration. You know that we have also discussed that the molecular orbital under Lekau approximation considers the ionic conditions of the molecule. Ionic conditions is overemphasized by the molecular orbital Lekau approximation, and due to that one there is a great separation between them, between the energies, and between the energies. And here we see that the energy due to Hitler and London method is quite close to the experimental value, that is minus 3.14 electron volt due to Hitler and London method is close to the value of the experimental value, which is minus 4.7 electron volt. And the difference between these two values is closer than the difference which is due to the Hitler and London approach, which is due to the molecular orbital under Lekau approximation. Now you see that we want to minimize these differences in binding energies also. That is, we want to have the potential energy curves due to these two methods, that is due to molecular orbital under the Lekau approximation, this method, and the Hitler and London method. We want that the potential energy curves produced by these two methods should be very consistent or should be very close to the potential energy curves obtained experimentally. And also their binding energy curves will also then be will be equal to each other, will be closer to each other, much closer to each other under improved approximations. So here we are going to suggest improvement to the approximations. We have the following wave functions obtained from equation number 73 for the case of molecular orbital method, and the real share of ionic configuration. You know that this is the ionic configuration in which the two particles can be either with the nucleus A, or the two particles can be either with the nucleus B. So this is there is a real share of the ionic configuration, and the ionic configuration is due to these two terms can better be quantified if a variable lambda in the range from 0 to 1 is introduced and we obtain. So you see that we are, in order to optimize the equation number 80 to give better results, we are going to introduce lambda and of course parameter constant C3. So we have C3, and then we have the square bracket containing A of 1, B of 2 plus A of 2 and B of 1. And you know that these two terms are actually the terms which produce ionic contributions. And then we have, this is the term with lambda, in which particle 1 and particle 2 are with either with nucleus A, or the particle 1 and particle 2 is either with the nucleus B. This is actually the term that contributes ionic contributions. So I have multiplied this term with lambda. So you can, now we have two parts separated by them, one containing the coefficient C3, the other containing the coefficient lambda. And we have to optimize the value of lambda to find the minimum energy. So C3 is the normalized constant. Lambda can be varied for each internuclear distance R. Each time you change the value of R, you need to optimize the value of lambda to make the total energy to become minimum. And the criteria is that we need to find the minimum energy. This would give a binding energy of Eb is equal to minus 4.02 electron volt. This is the remarkable improvement with respect to the simple molecular orbital Lecoq approximation. So you can see that this is value minus 4.02 electron volt, whereas the experimental value is minus 4.7 electron volt. So now you see that under the improvement condition, the molecular orbital under the Lecoq approximation is producing a result which is minus 4.02 electron volt, which is relatively much closer than its previous unimproved version. So this improved version is giving a better results, better binding, better potential energy curves, and also better binding energy curves. So far, I have not talked about the potential energy curves, which I shall be talking about soon. Now I have the Hitler and London wave function obtained from equation number 74. This can be improved by introducing ionic contribution through lambda. As a result, identical to equation number 81 can be obtained. And you know that here, if you introduce the ionic contribution, which means that again, Hitler and London is also introducing the same these terms. That is lambda times a of 1 plus a of 1 into a of 2 plus b of 1 and b of 2. This term with lambda is also included, but is also considered by the Hitler and London method along its original wave function, which is given in 82. And of course the results, this can be improved by further by introducing ionic conditions through lambda, as I have discussed, and as a result the identical to equation number 81 can be obtained. So the results, when the Hitler and London method approach included the ionic contributions, its approach gave the same result as given by equation number 81. That is both the molecular orbital under Lecoq approximation, under improved Lecoq approximation, yield the same result under the Hitler and London improved calculation or improved approximation, which includes the ionic contributions. The results of potential curves and binding energies are still different from experimental results. Further improvements can be obtained through the following considerations. You see that we have found that the binding energies in the improved method that we have discussed earlier, due to molecular orbital Lecoq approximation and the Hitler and London approximation, they have binding energies much closer to the experimental binding energies. But we notice when we plotted their polarization curves, when we plotted their potential energy curves, we noticed that their potential energy curves are even deviating from their experimental results. So further improvements can be obtained through the following considerations, so that their potential energy curve also become identical to those of the experimental data. So far, we have considered the wave functions using linear combinations of undistorted atomic 1s wave functions with the spherical symmetry. When the two atoms approach each other, the electron charge distribution will be distorted due to interaction between the two electrons and between the two electrons and between an electron and the nucleus of the other atom. It will be no longer spherically symmetric. That is, the 1s atomic orbitals that we have considered so far, these spherical 1s orbitals will no longer be symmetric when the atoms are closer to each other, due to the repulsive force between the two electrons and also due to the interaction of these electrons with other nuclei. That is electron 1 influenced by nucleus B and the electron 2 influenced by nucleus A. So it will be no longer spherically symmetric, but is distorted and also contracted. The actual wave function should accommodate the two 1s atomic orbitals. That is, this spherically symmetric orbital should also consider the distortions, because here this wave function that we have been using considers only that the 1s atomic orbitals are spherically symmetric. So in order to produce more accurate results, we need to consider that they are no longer spherically symmetric and are distorted and also contracted. For that one, we are using some non-spherical atomic orbitals also, defined in equation number 84 as phi of Ri is equal to the summation of over n wave functions C, K and phi of K. So you see that we shall add all these non-spherical atomic orbitals to the previous wave function shown in equation number 83. We can combine their both contributions can be combined, or this contribution due to equation number 83 can be considered to be contained in equation number 84. And in addition to that one, equation number 84 contains non-spherical atomic orbitals. Phi of Ri includes all possible contractions and distortions. The molecular orbitals for the two electrons can now be written as. So for the two electrons, this can be written as phi of R1 and phi of R2. But you know that under the molecular orbital Lekau approximation that we are introducing over here, that we are including the non-spherical wave functions also, non-spherical atomic wave functions. We have written this as a wave function of the molecular orbital Lekau approximations. Under second improved approximations is phi of R1 R2 is equal to summation over I and k, and containing Cik and phi I of 1 and phi I of 1 and phi k of 2, which means that the electron 2 belongs to phi k and electron 1 corresponds to phi I, and these are the normalization constant Cik. So you see that this model of the molecular orbital Lekau approximation, improved approximation, contains non-spherical atomic orbitals as well. This is the Hitler and London approximation. So actually this equation, which is phi of R1 R2 is equal to phi of R1 and phi of R2, is written for the two electrons under molecular Lekau approximation. So please correct that this is the wave function due to equation number 85, and due to equation number 85 is actually the wave function of the molecular orbital under improved Lekau approximation for the two particles, for the two electrons, phi of R1 and phi of R2, where phi of R1 and phi R2 is given by equation number 84. And for the Hitler and London approximations, the same wave functions in more generalized form is given by phi of R1 and phi of R2 is equal to summation over Ik, Cik multiplied by phi I of 1 and phi k of 2, which means that phi electron 1 corresponds to, is associated with the wave function phi I, and electron 2 is associated with the wave function k or with the nucleus k, and electron 1 is associated with the nuclear I. So this equation, that is equation number 86, is the Hitler-London approximation. The coefficient C, which gives the relative contribution of the atomic orbitals to the total molecular wave functions, are optimized in such a way that the total energy of R becomes a minimum for each selected internuclear distance R. That is, for each value of R, you would like to minimize this wave functions for the energy. The optimization is done through the following equation. So in order to optimize the equation number 5, equation number 86, you perform this calculations. That is partial derivative of the integral of phi star H operator, H Hamiltonian, phi and t tau, integral of this one with respect to the partial derivative of Ci should be set equal to 0. And the solution of this equation will give you the values of the parameters which will optimize the wave functions and which will also optimize the potential energy of the method due to the Hitler and London to correspond to the value of the experimental data. These n equations for n coefficients Ci. These are the n equations for n coefficients Ci. As R is fixed, while optimization, E of Ci is also a function of Ci. 13 wave functions phi I gave a binding energy of EB at its equilibrium value to be equal to minus 4.94 electron volt at the, of course, at the minimum of the potential energy curve, which is close to the experimental value. Colos et al. Used 50 wave functions phi I defined by equation number 84 and obtained the binding energy at its equilibrium position to be equal to minus 4.7467 electron volt, which agrees with the experimental value of EB experimental is equal to minus 4.7470 plus minus 0.0003 electron volt. The accurate total energy calculations of the simplest neutral hydrogen molecule requires large computers because we have to consider large wave functions. The basis wave functions of phi k should be obtained using physical intuition. You know that we have talked about the wave functions phi I and phi k, and of course these are the basis wave functions, and in order to choose these wave functions we use physical intuition. Potential curves of the hydrogen molecule, ground state molecule obtained under different approximations are shown on the next page. The binding energy is equal to 0 is the energy of the separated hydrogen atoms. The plot shows the results of the binding energies obtained under different approximations. So let me read again. Potential curves of the H2 ground state molecule obtained under different approximations are shown on the next page. So let me move to the next page. So you see that here I have shown the binding energy, here I have shown the potential energy curves for different methods. The solid red curve is due to Lekau molecular orbital approximation, simple Lekau molecular orbital approximation. Not simple, but the improved molecular orbital approximation. So the solid curve is due to the improved molecular orbital Lekau approximation. The green curve is due to the Hitler and London method. The red curve is the improved Hitler and London method. And the dotted curve in black is the exact method. And you know that here EB is equal to 0 is actually the binding energy curve due to the separated atoms. That is when R is very large, you approach the binding energy equal to 0 because the atoms are so large that there is no fraction of a binding energy. So you have a binding energy equal to 0. So potential curves of the hydrogen ground state obtained from different approximations. EB is equal to 0 is the energy of the separated ground state hydrogen atoms. That is in the molecule H2 molecule. When the two atoms are very well separated from each other, then of course the binding energy of such a molecule will be equal to 0. But you know that here we have discussed, you can see that the solid curve due to improved molecular orbital Lekau method, due to improved molecular orbital Lekau approximate method is even much deviating from the exact method. The Hitler and London method shown in green is close to the exact method, and the improved Hitler and London method is much closer to the exact method. You can also read it from the scale of the binding energies, that the binding energies are not very much changing for these curves. So let me read this paragraph once again. Potential curves of H2 ground state molecule obtained under different approximations are shown on the next page, which I have explained. EB is equal to 0. EB line equal to 0 is the energy of the separated ground state hydrogen atoms. That is, at a large value of R, the H2 molecule splits into individual hydrogen atoms and the binding energy is 0. The plot shows the results of the binding energies obtained under different approximations. Potential curves of the three approximations, molecular orbital, the Lekau approximation, Hitler and London, and improved Hitler London curves are shown and compared with the exact solutions. So you know that this lecture is still continued. That is, I shall still be talking about more about the molecular part of the hydrogen molecule. And you know that now this lecture is continued, and this is the end of the lecture number 18C.